Yeah, hey everyone. Thanks for joining us for the first kind of event of this sort that we're organizing on our Discord. Hopefully the first of many to come. I just want to say like a quick few words about, like what we're trying to do here. So obviously, Lido has a very large share of stake on Ethereum, but at the same time, we're also trying to give as much back to the staking community as possible. So as a part of the grants that we are giving out through our Lego sub-DAO, we engaged Miga Labs, a bunch of amazing researchers from a university in Spain, to take a look at Ethereum Consensus Layer clients and look at them from several different prisms, basically. From a hardware perspective, from a performance perspective, from a syncing perspective, a user friendliness perspective, and a scaling perspective. So we're joined, as Casper said, by Dr. Leo Bautista, who's going to walk us through the analysis that they did, and also open up during the presentation as well as at the end of the presentation for any questions that you might have. Thanks, everyone, and enjoy.
And on that note, off you go. The floor is yours.
Thank you. Can you hear me well?
Yeah, it's perfect.
Okay, good. Okay, thank you very much for the introduction. I would like to mention that this is a teamwork. My coworkers, Tarun and Mikel, are also present here. So if you have questions, please feel free to ask anytime in the chat. And if I cannot see the question, they will also try to answer in real time. Yes, so this is a work about the Ethereum 2 consensus layer clients. And as Izzy mentioned, the objectives of this work is to study how the different Ethereum 2 consensus clients perform. So we have 6 main clients that we wanted to test. I'm going to introduce them in a minute. And we evaluated the hardware resource consumption, so CPU, memory, disk, network, etc., about how they perform, these different clients. And for that, we tried different hardware devices, specifically 3 types of nodes that I would introduce in a second. And the idea was to run these experiments under different configurations. So the default mode, the all subnet topics configuration, the archival mode, and so on and so forth. And we also try to evaluate the user experience, the friendliness, the documentation, which are more, let's say, less quantitative, but also qualitative aspects of this analysis that I think that are also important. So at the end, I would present a table in which we try to summarize the good things and the bad things of the different clients. Now, these are the client versions that we use for all of them. So it's important to mention this because, the client teams are working really, really hard and they are progressing really fast. So they are releasing versions all the time. And actually, during this study, during the several months that this study lasted, we saw new releases of different clients, and we had to stick with the ones we were using, or we decided one and stick with the one because, if we change every time they release a new client, then basically we can never finish the study. So hard they are trying to make progress on many things. So all the results that are presented here are for the specific versions that you see right now on the screen. Now, the different hardware devices that we used were these 3 ones. The Raspberry Pi 4B, which has 4 cores, Cortex A72. Memory, it has 8 gigabytes of RAM, 256 gigabytes of disk, and the network was 100 megabits per second. And then we use 2 different types of cloud nodes. The standard one has 4 vCores, 15 gigabytes of RAM, 100 gigabytes of disk, and 256 megabits per second for the network. And the Fat Cloud node was a much larger node in which you had 32 cores, 120 gigabytes of RAM, 400 gigabytes of disk, and 10,000 megabits per second for the network. Okay, so these are basically 3 different types of nodes that we used. Now, this was a really large study. So, as Izzy mentioned, he, contacted us several months ago, and we started this, long time ago. We developed a whole document detailing all the things that we wanted to study, and I think we started the experiments around March. So most of these experiments were done in March and April. And definitely all of them were done before May. And we collected, so we run these experiments for 29,000, almost 30,000 CPU hours, which is about 1,243 CPU days, basically 3.4 CPU years. So this is really a lot of experiments that we run. And we collected about 108 million data points for Node Exporter. So we use Node Exporter to get as many metrics as possible. I will show some of them today. We also run our own Python script that also monitors everything: CPU, memory, disk, network, bandwidth, etc. And we actually compared that the Node Exporter numbers and the Python numbers were giving exactly the same performance. So that basically this was our way to cross-check that all the numbers that we were getting were correct, because we were using two different, completely different tools. One that we program, one that is that we found online, and we measured and we compared them, and we got exactly the same results. So this is to check that, to say that we check and cross-validate the data that we got. Now we also use a validator monitoring pool that we have been kind of co-developing with a friend of us, Alvaro, that I will mention at the end, that uses that we collected 2.3 million data points on that. Our Archival API Benchmark collected about 10 million. So in total, it's about 146 million data points, from which we plotted about 146 millions. I have to say that many of the runs crashed, many of the runs were repeated, so that's why we focus on these 146 million data points. And still, we plotted almost about 1,000 figures, and we put them all online for everyone to see. All the data is public. Please visit this website. You can see all the figures. I, of course, will not have the time to go through all the figures in this talk. I'm just going to present a few ones, but I think the most important that give you an idea about how these different clients behave. But again, please feel free to access this webpage and play with the figures. I think it's going to be interesting. Now, I want to say this disclaimer. The purpose of this study is not to find the best consensus layer client. We are not in this business. What we are trying to say is to do with this study was, first of all, we wanted to provide as much feedback as possible to all the developer teams for their respective client. And I think they have been able to make some progress and work on different features that we have been asked to them, or fix some bugs that we have found. And that was one of the purposes. The second purpose was to let the Ethereum Foundation know how the client consensus layer clients behave when they are, use it in mainnet, but also on the kill testnet when running with another, with the execution layer client, Geth or other. And also to provide information to operators, like Lido and other staking pools about the different clients, how much diversity they have, how much choices they have, and so that they can make decisions about what is a good fit for their specific needs. Okay, so this is basically the idea of this study. Now, with that said, let's start with the results. So first of all, I want to start with the CPU, memory, and disk and network. All these results were done on mainnet. Okay, so this is the Bitcoin chain. And so what you see here, for example, for CPU consumption, by the way, as I said at the beginning, I'm going to focus mostly on the 5 open source Ethereum clients because they represent, I think, the large majority of the current distribution on mainnet. However, I will present some results with Grandin as well. I will show you that later. I think what you see here in CPU usage, so you have on the x-axis, you have the slot. And this is, so as you can see, synchronizing from Genesis until the time where performed experiments was in April, I think, this one. And so this is until the slot 3 million something. And on the y-axis, you have the CPU consumption. So what you see here is basically the CPU consumption for all different clients. You can see that in yellow, you have Teku. In red, you have Prism. In blue, you have Lighthouse. In green, you have Nimbus. And in purple, you have Lodestar. And we will keep the same color coding through the entire talk. And through the website, you'll find the same color coding so that it's easy to understand the results, okay? And what you see is that at some point around slot 2 million something, you see a change in behavior on CPU consumption for most of the clients. And the reason why this happens is because this red line that you see here represents the Alter hard fork. Okay, this also is observed in the memory, as I will show you in a second. Okay, but then it's a clear transition to a different, different thing, and this is because, of course, you have to keep track of different things from alter. You have slashing conditions that have changed a little bit, slashing protection, and also different reward systems that you have to take into account. And so this is why you can see that the clients behave a little bit better, different after alter. Now, on the right side, you have a figure that shows the CPU consumption after syncing, and this is on kill network. This is not on mainnet. But what you see is that they perform differently. So actually, in the left figure, you already see that at the end, the CPU usage drops for all of the clients. And this is because after you finish syncing, of course, you need much less CPU resources, and that's why you see this at the end on the right. And then for the test on kill network, you see that most of the clients require less than 20% of CPU for running after syncing. Now, we were doing an experiment here in which every 12 hours we were adding 10 validators in the same node for each one of these clients, okay? And so this is why you see these kind of waves, in particular for Nimbus, because for Nimbus you have to restart the beacon node because it's the same executable as the validator client. And so you see these waves every 12 hours, we increment the number of validators. And curiously, you can see that for Lodestar, as you increase the number of validators, the CPU usage does increase a little bit. So it's interesting to see that you have to take into account that if you want to scale to many validators with Lodestar, you should be able to, you should check about CPU consumption. Now, for most of the other clients, they remain pretty much constant as you increase the number of validators. Now, if we go to memory, you can see that, again, in yellow you have Teku. Here we had some issues with the GVM. It's not always easy to fix the right amount of memory for the GVM, so we had several crashes until we managed to get it right, and then it was stable for the rest of the run. In red, you can see that Prism increased the number, the amount of memory it consumes as you are syncing. This is again syncing from Genesis, and you see a jump here at some point in slot 2 million something, and this is again the alter hard fork, right? And this is because you have to keep track of other things. Then you need more memory. That's visible on Prism. It's also visible on Lodestar, which actually almost doubled the memory consumption from 2 gigabytes to 4 gigabytes. Okay, and for Lighthouse in blue, you can see that the memory consumption really increases a lot. Actually increases to some point that it reaches the limit. In this case, was 50 gigabytes, and then the client crashed. So we had to restart it, and then we can see that the blue line starts on the bottom again. We talk about this with the Lighthouse team, and they are working on it. They're investigating what is going on. This is probably some memory leak. Maybe it's already fixed in the last release. I'm not sure about that, but anyway, I'm sure that we discussed this in April with them, and they were analyzing this. So again, but after synchronization finish, this kind of memory behavior changed completely, and it became much more stable. So basically, I'm not sure this is so big of an issue for Lighthouse. For Nimbus, we see that it's a very, very low memory consumption. It's actually the lowest memory consumption from all these clients. So I think it has been optimized really to be able to run in devices with low memory. Now, if you look at disk usage on the right, you can see that they all have really different disk usage. And they are really different. So, for example, if you compare Lighthouse to Teku, it's almost 3 times more. It requires almost 3 times more storage than Teku. So that's also something that is important to take into account while you decide which client you want to use. Now, when you look at disk operations per second, you have disk writes operations per second on the left and disk read operations on the right. Now, on the left, what you see is that at the beginning, when you start syncing, you do many disk write operations per second. In particular for Prism, this is very visible. And the reason why this is happening, I think, is because at the beginning, you have very, very few number of validators in comparison to today. So you had less validators, that means less attestations, that means you can process more blocks quickly, right? And so because you can process more blocks quickly, then you have many writes going on at the same time, okay? But as you progress in time and you are syncing through the epochs, the number of validators increases, and therefore you have more things to do, and it takes more time to validate to process a block, and therefore the number of write operations per second decreases until it becomes stable, which is the last part on the right side of the figure. Now we see this behavior for almost all the clients. However, for Prism is the one that is more marked. And then on the right you have the disk read operations. Now this is something that it was quite puzzling for us because we detected that at some point around slot 1 million or so, the clients started to do a lot of read operations, okay? And it kind of starts suddenly and it goes up. I think the most clear in here is the case for Prism. They still perform well. I mean, this is not necessarily an issue, but it's definitely interesting to see how about at this slot, they start to perform more read operations. And the same happens for almost all the clients except for Teku. It's the same for Lighthouse, it's the same for Lodestar, and it's the same for Nimbus. It's not as visible on this figure because there's just too much things going on this figure. But if you isolate one client alone, you will see it, and you can go to the website and see it, and you will see the same pattern. And it was curious for us why this happened, and it happens for almost all the clients. We discussed with the client teams. One thing we noticed is that if you do the same experiments in different nodes, this is what you observe. So on the left, you have the same experiment on the Raspberry Pi, and you see that the disk read operations start much earlier. It kind of already from the slot 400,000, you already see that it starts going up. In the case of the Dark Cloud, it happens around 1 million. And in the case of the Fat Cloud, it starts around 2 million, and it's not even as marked as is for the other two cases. So I think what is going on here is that there is some kind of buffering or some kind of catch thing going on here, in which as far as you have memory, you don't need to access the disk, right? But at some point when you run out of memory, and this is visible in these three devices because you have 8, 15, and 120 gigabytes of RAM, then you start performing a lot of read operations, okay? So I think this is what might be going on. However, we have discussed this with the teams, and they are also investigating it to see a little bit more clearly into why such pattern occurs. Now, concerning network activity, I want to show two things. So here on the left, you have the peers, the number of peers for each one of the clients. So, for example, you have Nimbus is the one that has, that runs with the largest number of peers. So it oscillates between 100 and 150, and you can see that it's very flexible. Okay, so that it's very elastic. You can switch between 100 and 150. And it's kind of elastic. In the case of Lighthouse, Teku, and Prism, they are less elastic. However, they have some margin, and they run with 80, 75, and 50 peers by default. And finally, you see the case of Lodestar, which is not flexible as much as the others. It's actually quite tight. You almost run with 25 peers all the time. You have a little bit of room to go a little bit up and down, but not much. So it's a kind of a very strict policy in the case of Lodestar. Now, when you compare this with network activity, so here on the right, you have the receive data in megabytes per second. And this is in the case of using all subnet topics, okay? You see that, for example, Teku is the one that uses more network bandwidth, right? And this is, and for example, here you have Nimbus that is the one that has more peers, but is not the one that is using more bandwidth. It's actually one of the lowest in terms of bandwidth consumption after Lodestar. But for Lodestar, it's understandable you have a low network consumption because it has also the lowest number of peers, and it's also a very strict policy in terms of number of peers, right? So this actually correlates. However, for Teku, it's actually a little bit high, in respect to the number of peers that they have and for Nimbus it's a bit low in regard to the number of peers that they have. So this is regarding network. But we also try to test the all subnet topics versus the default scenario. Okay, so this is a little bit of a busy slide. Let me go through it a little bit quickly. You have, again, in red is Prism, in blue Lighthouse, in yellow Teku, then you have Nimbus, Lodestar, and at the end you have Grandin as well. And you have on the left the received data, and on the right the sent data. Okay, and then on each figure you have two lines. The light line, light color, is the configuration in which you're running on default mode, and then the darker color is when you run with all subnet topics allowed. Okay, so what we see basically for almost all the clients is when you allow the option to run with all subnet topics, of course, as expected, you see a much larger network bandwidth, both for data received and data sent. However, in the case of Teku, is much higher. Now, if you look at the figures, you might say, oh, no, but it's almost the same as the other. It is not, because if you look at the y-axis, please pay attention that in the case of Teku, it goes up to 200, while in the case of Prism and Lighthouse, it goes to 100. It's same for Nimbus. In the case of Lodestar, it goes to 50, which means that it's really, really low. Now, there is something weird with Lodestar, though, and is that the sent data on default, it seems to be higher than the sent data on all subnet topics. So this is something strange that we are investigating. We commented this with the Lodestar team, and they are trying to reproduce this or trying to look into this. It could be a bug. So something strange that we are trying to analyze there. And for Grandin is a low network consumption, bandwidth consumption, and again, of course, the same pattern. You use more bandwidth when you allow all subnet topics. Now, regarding syncing speed, we want to compare the standard node versus the fat node, and this is, of course, on mainnet. Here you have the syncing speed. So on the y-axis, you have the slot, and this is on millions, so it goes from 0 to 4 million. Okay. And then, of course, in the x-axis, you have the time. So see, this is the time in hours. Now, you can see that Nimbus syncs, for example, in about 75 or 73 hours. And Prism is also very close. So here, among all these 5 clients, Nimbus is the fastest one to sync in comparison to the other 4. And then Lodestar is the slowest one. Okay. Now, this is kind of a little bit of controversial topic. Many people say that syncing speed is not even relevant because now you should always use checkpoint syncing because it's more secure, and also because syncing is just like 1% of the lifetime of a validator. After you sync, you never had to do it again. So it's not even relevant on that case. However, since we had to sync all the clients, and since this is still, I think, the most used way to sync today, that's why we present these results. Now, what you see on the figure on the right is the number of slots per second. So the higher, the better. And again, you see a similar pattern that with the write I/O operations. What you see is that at the beginning, it's very easy to process blocks, so you process many blocks very quickly. And this is again because you had less validators on the network, therefore less attestations, therefore everything goes faster. But that quickly goes down, and then it becomes flat. Okay, and that's what you see this kind of pattern here. Please notice that here again, Nimbus is the first one to finish syncing, then Prism, then I think Lighthouse, Teku, and at the end you have Lodestar. Now, but here I wanted to mention some experiments that we did. That here is important to include Grandin because this experiment is on the fat node, so it's the large node with 32 cores and 120 gigabytes of RAM. And I think this is important to show because they really show an impressive performance here. It actually syncs 3 times faster than Lodestar. And way faster than all of the other clients. So I think the Grandin team has done a lot of effort on parallelizing and making sure that the state transition is really, really fast. and that is visible in these figures. Again, if you look at the left figure, slots per second, you can see that Grandin processes slots much faster than all the other clients, and in particular in this fat node, that's even more visible. Okay, so yeah. Now, regarding the experiments on the Raspberry Pi, I want to show just a few things because I won't have time to go through all the details. But basically, just to try to show the CPU usage and memory usage of all the clients on the Raspberry Pi. You can see that in comparison to the previous figures, the CPU consumption is higher than on the other nodes, which makes sense, of course, because you are in a kind of low power device, and that's why you see this kind of behavior. But however, all of them managed to run properly on a Raspberry Pi, so I think that's good news in terms, thinking about decentralization. That means that anyone can run any client on a Raspberry Pi at home or something like that. Now, in terms of memory usage, again, of course, the memory usage is much higher, than in the other nodes, but it still managed to run properly. All the clients run well. Again, for Nimbus, you see a very low memory consumption, even in the Raspberry Pi, again, because they have optimized for this, apparently. Now, we also tried to evaluate the archival mode of the different clients. Okay, so Lodestar and Grandin do not support or do not have a client archival mode at this point. So we focused on Prism, Lighthouse, Teku, and Nimbus. On Prism, I have to say that we didn't finish syncing by the time we were doing these experiments. So it's normal that the success ratio was not 100%, and this is because probably many of the requests that we were doing, the block was not even in the in the database yet. So please don't focus too much on the success ratio of Prism here. But just try to explain what we did. We execute a random query every 10 seconds. And the exact query is the one that you can see here. So that if you want to try the same, here is the query. And when I say random, it means that it always asks for a different, random beacon state number. And this is because we didn't want it to make it sequential, because we wanted to stress the database as much as possible. The client as much as possible, and see how they perform. And so on the right, you see a figure that shows the response times distribution. Okay, so you have the median and the quartiles. And you see that for Prism, you have about 13 seconds in average. Lighthouse is about 3 seconds. Nimbus is about 5 seconds. And I think Teku is about 2 seconds. And I have to mention that Teku is actually, the variance is very low here. Meaning that this is a very robust and fast response time for Teku. We talk about this with Teku team, and they explained us that they have optimized the database. They have developed a different kind of a tree structure that allows to save basically the states in a very, very optimized way. The reason why they did this is because, they are part of Consensus, so they work with I forgot the name. They need a database to Infura. Sorry, yeah. They work with Infura, and so they need a really, really fast structure that can have a very, very low response time. So I think this is visible in these experiments. The code for this API benchmarking tool is available online. I will add the link at the end of the talk. So very, very fast Teku, quietly, good for Lighthouse and Nimbus as well in terms of response times. Another thing that I want to mention here is that Prism uses gRPC instead of the HTTP API, and so that's why probably there is this kind of translation overhead going on, and that's probably one of the reasons why they don't have as good performance as the others. Now, I want to discuss a little bit through the strengths and weaknesses of the different clients, and not only focus on the quantitative measurements that I have already presented here, but also including the qualitative aspects like documentation, friendliness, etc. Okay, so starting with Prism, I think according to my team, I think from our perspective, it has the best user experience among all clients. It's a client that is extremely easy to use and deploy. It's very easy to work with. So I think the team has done a lot of effort in maximizing the friendliness of this client, and I think that is visible in the share that they have on the network, right? Now, on the bad side, I think we can say that the search function in the documentation didn't work very well for us. It could be improved. And again, regarding the archival mode, they use gRPC calls instead of the HTTP API, and I think that hurts a little bit in performance for the archival mode. Okay. Regarding Lighthouse, I think it has the most complete Ethereum 2 Beacon Node API. It was so good that it was the one that we use for the reward analysis that I'm going to present in a minute. So this is something that is really, really good in this client. On the bad side, apparently they have some memory leak that happens during syncing from Genesis. It doesn't show later on, but it could be already fixed in the latest release. This is something that we haven't tested yet. But yeah, so this is something that we observed during our experiments, and we actually reproduced it several times. Yeah. Now, it also has a very large disk usage in comparison to other clients. Actually, during our experiments, we had to change and allocate more volumes, bigger volumes for working with Lighthouse because of this reason, because at some point we ran out of space. Regarding Teku, it has an excellent online documentation. It's very complete. It's very easy to find any flag, any configuration that you need. So really, really great documentation. It has a low disk requirements. So and the interesting thing is that they also have the fastest API response on the archival mode. So they have worked on that, and those optimizations are very visible. On the bad side, we had issues with the GVM memory management. It's not always easy to set up correctly, and then that leads to crashes, which can be a little bit annoying at the beginning. Once you set it correctly, it's very robust. It also has some kind of high CPU and network consumption. Now, to be fair, the team from Teku has released a statement in which they mentioned that the latest release improved CPU consumption by 25%, if I remember correctly, and also reduces network consumption by 40%, if I remember correctly. So again, as I said before, it's a moving target. Every release has improvements, but this is what we measured during our study. In the case of Nimbus, definitely fast syncing client from all the open source was the fastest one. And it has very low CPU usage, very low memory consumption. They have optimized the client for not only low memory, low power devices, but also for cloud servers. And we can see that those optimizations work well. Now, on the bad side, it's not as user-friendly as other consensus layer clients. And it has this feature that it could also be a disadvantage, and is that the beacon node and the validator client run on the same executable. Now, I think I understand that they want to simplify things by having just one executable, which it does on some aspect. But it can also be a disadvantage because sometimes you want to have the beacon node running while you restart the validator client, for example, for adding new keys, new validators. And this is something that we observe in our experiments, so this is something to mention. That said, they also mentioned that they are working on making the experience more user-friendly, and they are planning to release a new validator client, separate validator client in the coming months. Regarding Lodestar, it uses fairly low resources in comparison to other clients, and it supports almost all the features of all the clients. And given that they are one of the latest, of teams to join the party, it's commendable to see that all the progress they have done so quickly. Still is one of the slowest client, and it is still missing a number of features. For example, it doesn't support archival mode, and so on. It also has some kind of outdated documentation. In many cases, we noticed that the documentation was giving instructions that were not up to date, and so that made the use of the client a little bit more hard to use. So this is something they probably should work on. Regarding Grandin, I think it's clear that it outperforms all the clients in syncing speed. They have used some kind of parallelization that leads to a fast state transition, and this is visible on the experiments. Of course, the biggest issue, I think, is that it's not open source yet. So this is something that we hope it can happen in the future. And there are several features that are not supported. Actually, during the experiments, we had to contact the team several times for specific experiments we wanted to do, and they were very quickly to answer and to give us an executable that was possible to test. But of course, there is still a lot of things going on. But again, they are one of the last client to join the party. So I think it's normal that they are still it's a work in progress. Now I want to do a sneak peek of what is coming. Some future work that we did on the Killing testnet, and is regarding attestation rewards. So we studied attestation rewards for all the 6 clients here, you see. And again, this is an experiment where we increase the number of validators, 10 validators every 12 hours. So we see kind of this, and the X and the Y-axis here is how much rewards do we get in millions, okay? And then what you see is this kind of stair behavior. But also please notice that at the beginning, when you have only 10 validators, the rewards are very stable. So it's a thin line. However, when you have 100 validators, you see that this cloud of dots you see more variance, right? And this is probably because as you increase the number of validators in the same node, you start missing attestations, and then you start losing rewards, right? Now, please also notice that there are some cases where, for example, Lodestar or Grandin or Lighthouse are doing more rewards, getting more rewards than others. This is just an artifact of the fact that one of the validators of this of this client got into a sync committee, and that's why they were getting more rewards during that period of time. Okay, but this is just an artifact of that matter. If we remove sync committees from the reward system here, you will see a clear stairway where all the validators are basically getting more or less the same rewards. We also have the number of incorrect heads on the right side. You see this figure. Again, you see that when you are running only 10 validators per node, there are not many incorrect heads. However, as you increase the number of validators per node, you start seeing more incorrect heads. Again, probably indicating that as you stress more the hardware and the network, you might start missing attestations or missing things. I think that's just a sneak peek of what we already started. So this is a project that we started, that we want to do, and we are starting to work on it. And we hope that we can have a full study in the coming months about attestation rewards. And I think regarding the result, that's pretty much it. I'm just gonna want to acknowledge the Lido Research Program grants, because of course this is what allowed us to do this research. Thanks to them, we have all these results that we hope are going to be used for the community. We also want to thank the Ethereum Foundation Research Grant. We have been research grantees from the program for several years already, and that actually was what we did, that would allow us to do the research paper that we did a couple of years ago on this very same topic, actually. We also want to thank OVH Startup Program for their support, all our Gitcoin supporters, which we had about 100 contributors in the last couple of years. And thanks to that, we have been able to also continue doing our research. I hope that you see that we continue working and we try to provide valuable data and information to the ecosystem. Thanks to all the Ethereum 2 consensus client developer teams. Honestly, without their support, this study will not have been possible. They have been super friendly to us, super helpful, and very responsive all the time for us to run their clients in the specific configuration, in the specific hardware. And with all their support, we couldn't have done this. So thank you very much. They had also been participating in the discussion and conversation of the results that we observed. And this has been really, really great working with them. We hope that all this information is valuable to them as well, and that they can improve their clients based on this. I would like to thank also all the many researchers outside the Ethereum client teams for many interesting discussions, and in particular, thanks to Alvaro, Rick, and Joe for their support during this study. Now, just to close, if you want more information, you have the previous research paper here, the detailed annotations about every single experiment we run, which command line, what we observe, errors reported, etc. You can find all of that in this HackMD. You have also our Medium post showing more or less what I have presented here, a little bit in less detail, but you have it there if you want. We also publish our Python script that you can use if you want to do the same experiments, you want to measure, disk, network, CPU consumption, and so on. You can use our tool. You can use our API benchmark tool as well. It's available on GitHub. You can use our Ethereum 2 validator client monitoring tool. Here you have the link. All the figures, as I said, are available in our website. Feel free to go there and play with them. And please visit our Gitcoin grant. And if you think this research is valuable, please support us so that we can continue doing more research. Finally, visit our webpage and follow us on Twitter. And I think with that said, I am done. If you have questions, I will be happy to answer. And thank you very much.
Thank you very much, Leo, for that exceptional walkthrough. It was really interesting to watch.
Thank you.
We don't have any questions in the chat as of yet. I'll give it a few minutes just to see if if anyone has any last minute questions. We've also posted all the or some of the relevant links and resources from your presentation that you referred to in the chat. So we encourage everyone to go check out these resources and to, of course, follow Miga Labs on Twitter for more insights here.
Yeah, and just in case you guys haven't found where the chat is, if you mouse over the Lido events channel, there's a little message dialogue, box. You can click it and it opens the chat. You can write your questions in there or raise your hands, and we can probably even turn on your mics.
Thank you. Thank you, Ray.
Not quite a question, but we'll take it for now.
Indeed.
How long did it take for you guys to put all this together?
So I think we started in the month of February, if I remember correctly. We started working with EC on detailing what we wanted to do. We wrote this document with all the plan, and I think we started experiments in March, and I think it took us about 2 months to run all of the experiments, more or less. Yes, about 2 months to do all these experiments. Yes.
Got it.
Then, of course, it was a lot of data analysis, plotting, et cetera, et cetera, et cetera. So, yes. And I have to say also that there are also other things that I didn't present here. I wanted to focus on the performance. However, we also did experiments on other aspects, like, for example, how easy is to transition from one client to another, exporting your keys and importing your keys to another client. We are doing this study, and we are going to probably release some report in the coming weeks. And so this is another part of the same project that we started with Easy, and it's coming soon. I just wanted to make it separated because to have the topics in different, to focus on this specific topic about performance.
Yep, that sounds good. We'll prepare another Discord event for that when the time comes.
Okay.
And where can viewers find that research when it's published? Is that on your Twitter or Medium?
So probably we will publish a blog post on Medium, yes, and we will probably tweet about it when it comes out.
Okay, Sounds great. Yeah, so no questions yet, but there are a lot of affirmative compliments.
Thank you. Thank you very much. Yeah. And of course, if somebody, comes up with a question, tomorrow morning or later, you can contact us on Twitter, or, you can find us here on the Discord, and we'll be happy to talk or to set up a coffee call if you have any specific thing you want to discuss. Of course, we are here.
Sounds good. We'll also share a recording of this presentation in the coming days, and maybe we'll get some questions off of that, and we'll send them your way. So. Izzy, do you have any final comments or remarks?
No. Obviously, it was a pleasure to work with Miga Labs. Like the quality of the research and analysis, as everybody can see, is incredible. I'm anxious for part 2 of the research that they're going to release, and also potentially working on them with them on future research topics. There's obviously a lot that we can look at in other realms as well. As we start to also look at execution layer diversity. So lots of really, really cool things that we can explore, and I'm excited about it.
Great. We're excited as well, Izzy. Thank you.
Okay. And I think on that note, let's wrap it up. Thanks for joining, everyone. Thank you, Leo, for taking the time to do this, and we look forward to part 2.
Great. Thank you.